Okay. Welcome, everyone, to the second Quantum Revolution in Space event. I'm so thrilled to be here. And in a minute, we are going to have an opportunity to meet two amazing guests in regards to this topic. But before we do that, I want to, first of all, do a bit of a shout out to a number of people that are actually joining us really from around the world, which this is amazing. We've got a great contingent of people, obviously, from Toronto and Calgary, but we have people who are joining us from around the world. Here's just a few places that are joining us today: Jakarta, Mumbai, even Paris. So we have really a global contingent to be part of this today, and we're looking forward to really the next hour and a half to 2 hours of conversation when it comes to the second quantum revolution in space. Now, before I introduce the guests, I have some housekeeping to do. And before I do that, I'm going to share my screen in presenter mode here, and we will get things started. So if you can bear with me, can you see my screen? Just give me a thumbs up in the chat. That would be great.
It's in the wrong mode. It's in the presenter mode instead of the presentation mode.
One sec. I will do that one more time. Give me a second. Thanks for letting me know. Bear with me, everybody. And we'll get this momentarily. Okay, can you see my screen okay now? Julie, is that okay?
I'm not seeing it.
Okay, 1 second. I will do one more thing. Thank you for the hiccups. Bear with me. And you're still seeing my presenter mode, I assume, that I can see on the screen.
Yeah. Yes.
I'll be right there. Technical difficulties.
There we go.
There you go.
Can see it okay?
Yeah.
Yes.
Perfect. All right. Wonderful. Well, first of all, welcome, everyone. Here's the first question I want to ask everyone. Have you ever wondered about the mysteries of space, the vastness of the universe, and what you see in the night sky? Right now, if it wasn't cloudy, you could see 4 planets in the night sky without a telescope: Venus and Saturn to the west. Here's another one: Jupiter overhead and Mars in the east. Uranus isn't far from Jupiter, and Neptune is near Venus. Events like this highlight the endless possibilities of what lies beyond our planet. Our imagination is that could one day become realities. And if this is the kind of thing that excites you, you might be interested in learning about Space Place Canada. We are a Toronto-based not-for-profit of space enthusiasts from various backgrounds and professions. Our leadership team includes astronomers, science educators, planetariums, and even space enthusiasts like myself. I am one of those. It's been shown time and time again that experiencing something like the planet parade that we just saw earlier, or last year's solar eclipse, particularly at an early age, sparks an interest in science. But at Space Place Canada, we want to highlight that spark. We want to be a place where the wonders of the universe are not just seen, but they are really felt, where the next generation of Canadians can really discover the infinite possibilities of science and exploration. And supporting Space Place Canada is more than just donating to a building like you see here, a concept. Right now it's a concept, but it's about the future of what we're trying to build. It's investing in the future of our children, our community, and even our country. My name is Daryl Kaneinenbelt. My day job, I work as a strategic communications professional, but as a volunteer, I'm a communications advisor for this great organization, Space Place Canada. And I channel my inner space nerd, if you will, to get to be part of a profound planetary purpose. Now, we're just not building a planetarium. We're creating an iconic Canadian institution, which will tell our nation's stories and really celebrate our achievements in space. We are building a place where all Canadians can come together to explore the cosmos, and that will inspire an education and educate generations to come. So you can find more about Space Place Canada and consider joining our group at the email above, membership@spaceplacecanada.ca. We, of course, want to thank our sponsors for their grateful support. You can see them on the screen: MDA, Nordspace, Pratt & Whitney, and Larson and Turbo. And now to the stars of our show. We're going to basically share these Canadian stories on cutting edge technology in which the very big meets the very, very small space. And that is quantum technology. Our event tonight is entitled, as I started, The Second Quantum Revolution in Space. And two guests on the screen joining us from Qubo Consulting. They are on a mission to facilitate the adoption of quantum technology, first by helping us understand just what it is and why it will rely on space. Katanya Kuntz on the left and AJ Sikora on the right. Katanya is an experimental quantum physicist and co-founder, CEO at Qubo Consulting. She's also a research associate at the Institute for Quantum Computing, University of Waterloo, Canada, and the KeySat science team coordinator for Canada's first quantum satellite mission. She's also a long-time Space Place volunteer. And then AJ. AJ is an edupreneur and co-founder, chief learning officer at Qubo Consulting with experience in business, education, and coaching. And with that, I'm going to stop sharing my screen because I'm going to hand it over to the actual stars of the show. And I want to welcome you both. It's been a thrill to learn a bit more about what you're doing, and welcome to the show, and welcome from everyone that's here today. For the run of show today, I know you guys have a really lengthy presentation. We're going to probably take the next hour and dive deep into quantum physics. I know we've talked about some of the background in regards to your topic. One of the first questions I had, and we talked about this even in our rehearsals, I'm assuming that many people on this call are academics, scientists, and enthusiasts. So I thought, let's start it simple. My first question is this: a qubit. What's a qubit? And how does it work? And I think I'm going to first ask Katanya Kuntz that question.
Well, thank you very much, Daryl. It's a little bit tricky to define what a qubit is technically without any graphics yet. It is part of my presentation, but in a very short elevator pitch type of snippet, a qubit is a quantum bit. It is a unit of information to store quantum information. So just like a classical computer, the computer I'm using right now to talk to you about all of this wonderful stuff, we use bits, and they save information in 0 or 1. So it's binary, right? With a quantum bit, it exists, these elements, they exist in a superposition state of 0 and 1. And so this opens up a vast computational space. You can attack problems that are not possible with our current computers, and you don't have to wait for a crazy big fault-tolerant quantum computer that might come in the future. There are systems now that use qubits that you can do computing now, and we'll talk about that later.
Perfect. Thanks for that explanation. I really do appreciate that. I'm looking forward to more of that. And I don't want to take it away from any of your presentation, but I have one question for AJ as well, and then I'll hand it over to you. And for our viewers, just for the run of show, what will happen is that after this last question, I'll hand it over to Katanya and AJ. We have a place where people can actually ask questions in the chat, so please do that. We will take them as we see fit. I'll probably interject a few times as well, ask some questions if something, piques my interest. And so I'm fascinated by this topic. But AJ, for you tonight as well, just high level, what maybe the top 3 things you're going to dive into tonight before I hand everything over to you?
Yeah, excellent question. I'm happy to be here, and we're happy to be promoting Space Place Canada and supporting Toronto and potentially getting a planetarium back. I was reading on your website that they haven't had one since I think 1995, which is a couple of years after I left and moved out west to Calgary. But for my presentation, I'm going to be talking about the job seeker's guide to the quantum industry. And this is kind of a preview of a course that we're going to be offering on our website soon. And in it, I'm going to give people an overview of how quantum could impact various industries across different sectors. I will talk about what kinds of quantum jobs are going to become available. And some are available now, and I'll show you guys that. As well, I'd like to just dive into a little bit of the investment numbers because I feel like for those of us that don't really know much about quantum or science or the technology side, we all understand numbers, and so I'll explain some of the investment numbers in terms of how much countries are investing into the quantum economy.
Great. That's a great introduction and for setting the table for us. So with that, again, welcome to everybody to the program. Feel free to put your questions in the chat. Remember, we are Space Place Canada. We are encouraging people to sign up for memberships. We are trying to build a planetarium, and it's with great events like this that make us possible to help us like channel that inner space side of us and to really learn from experts like Katanya and AJ. So over to the both of you and take it away, and we will enjoy your presentation. And if we have any questions, we'll pop in.
Excellent. Thank you so much, Daryl, for that amazing introduction. As I mentioned, we're thrilled to be here and thrilled to be supporting Space Place Canada. Just give me 1 second here, please, to get my presentation up. Okay, and Katanya, can you give me a thumbs up if that looks good? Oh,
I'll just say it. It looks great.
All right. Thank you so much. So, welcome everybody. This is the Quantum in Space webinar. It's a collaboration between Space Place Planetarium and Qubo Consulting Corp. And so we're here from Qubo to support Space Place and encourage you to make donations. Join them as a member, help them in their endeavor to bring a planetarium back to Toronto, as I mentioned. So I'm going to kick things off here with a presentation. This is a preview of a course that we're going to be selling on our website very soon. We were aiming to have these up in the fall last year, and so they are very close to being ready to put up. So once again, I'm AJ Sikora. I'm the co-founder and chief learning officer here at Qubo. Qubo is a business that we're interested in growing the global quantum ecosystem through training and consulting. And so we want to help remove the barriers for people and businesses to get involved in quantum tech. And so the best way to start is by learning about what are some of the potential impacts that quantum could have. And so this presentation will show you that. It'll also help out job seekers, anybody thinking of transitioning industries, anybody thinking about upskilling, anybody who's just interested in being the quantum advocate in your organization. This presentation is for you. All right, so I know Daryl already welcomed everybody, but welcome again, everyone. Truly, everybody is welcome here in all of our courses. We really appreciate it. Having people have an open mind, don't worry too much about understanding anything that's too technical. There might be a couple of things that we dive into a little bit, but we'll let you know when we're going to dive, and then we'll come right back up to the surface right after. So I'm AJ Sikora. My background is in education as well as business. I call myself an edupreneur. And I like to focus on helping people learn new concepts. And so that's kind of what I've dedicated my career towards. And so I help with translating dense technical scientific information so that regular everyday people can understand it. And Katanya, would you like to do a brief intro of yourself at this point?
Yeah, sure. Hello, everyone. I'm Dr. Katanya Kuntz. I'm an experimental quantum physicist, and as you heard, the CEO of Qubo. I also have a position with the University of Waterloo at the Institute for Quantum Computing, and I'll be talking a little bit about my research with them and the KeySat mission later on. So I've been in the field for a while. I've got an undergrad in physics and a PhD in electrical engineering. So if there's any engineers on the call, hopefully I'm a good translator for you. And if there's any hardcore physicists, I'm there for you too. Thank you.
Excellent. Thank you, Katanya. Let me click on the right window here. There we go. Okay, so as I mentioned before, please keep an open mind. It's really important to just be open to learning and willing to learn about quantum technologies. It's not all that scary once we get into it. The thing I like to focus on, because my background isn't in quantum either, so what I focus on is the big concepts. What should I take away from this presentation? So, if you have questions, please submit them. I believe there is a question function on YouTube that you can submit them to, and we have people that can relay the questions to us here. Okay, so what this presentation is not. Okay, so this presentation is not robot butlers, doom and gloom, and tin hats. Okay, this presentation is only credible, legitimate information, and we're not focusing on those kinds of things. So here's an overview of the presentation today. So in section 1, I have the intro to quantum tech. In that, we'll talk about the quantum threat, some quantum solutions, as well as potential industry impacts. Then we have section 2 with the quantum workforce, and we'll talk about the quantum workforce, jobs, as well as training. And then in section 3, we have the quantum global market, and we'll talk about global investment in quantum and notable quantum investments. All right, so the quantum threat. So many people have heard about the quantum threat, but let me just explain it to those of you that haven't heard. So quantum computers are expected to be exponentially more powerful than classical computers. And with that power, there's the fear that we could have a quantum system that is so powerful that it could break some of the current encryption standards that we use today, such as elliptical curve or RSA. The expectation in general from the industry is that in roughly 5 to 15 years, we will see a major break in our encryption due to a quantum threat. Now, like that's bad enough as it is, but I'm just going to add a little bit here about the harvest now, decrypt later. Some people call this a handle threat. Some people call it something else like steal now and decode later or something. But harvest now, decrypt later refers to the threat that foreign actors could be stealing our encrypted data today and storing it, and then just sitting on it and waiting until they have a quantum system that can break that encryption and they can access the data. So that might be an issue for some organizations. It might not be an issue for other organizations, but if you have a long lifespan on the sensitivity of your data, then that could be an issue. And I'll just mention this word hype. So there is a lot of hype surrounding quantum technologies. Some say way too much, some say way too little. Here at Qubo, we try to just give you the middle of the road, honest answer, what is actually happening in the quantum industry. Okay, so we talked about the doom and gloom quantum threat. Now let's talk about some quantum solutions and potential impacts in industries. So why is quantum so powerful? Well, quantum matter behaves differently than the way that things work in the classical world. There are special properties that exist when you get to that tiny, minute scale that can be harnessed and utilized to create new and potentially more powerful technologies. Here are some of the exciting things that quantum technology could do. Okay, so I'm going to start off with data security. I know we're talking about quantum and space. That's coming up, don't worry. But I can't leave you hanging because we were talking about the quantum threat, and I want to talk about some potential solutions here too. So with the quantum threat, the data security industry could have large implications, right? Like if say a healthcare company had a ton of data that was, medical data about people or something like that, that's data that doesn't really expire. It has a long lifespan. So we want to be able to protect that data. So we do have two solutions, I should say. One of them is quantum. That's quantum key distribution, which is a theoretically 100% secure form of communicating. The other solution is called post-quantum cryptography, or sometimes people call it PQC. And what that refers to is using a more robust algorithm. It's still a classical algorithm, but it's supposed to be more robust and resilient towards both future classical threats as well as future quantum threats. The issue with that is we don't actually have a quantum system to test them with, but we do have a little bit of an idea as to where to begin with those algorithms because in the summer, the US released 4 algorithm candidates to be used in post-quantum cryptography. Okay, let's move on to space. So I've split this industry up into 2 slides. First, I'd like to talk about quantum for space. So ways that quantum technologies could help out the space industry. So in computing, we could see some optimizations. Maybe the fuel used in rockets could be improved, or the placement of satellites, like figuring out a satellite constellation so that you need the minimal amount of satellites to cover the maximum amount of area. We could see simulations as well. Some of the more complicated systems that we deal with could be modeled potentially using a quantum simulation. And so we could look at things like weather modeling. We could look at launch trajectory or orbit of a spacecraft or satellite. As well, we could look at modeling planetary environments, like foreign environments, like on Mars or somewhere else that we can't actually physically get to. And then in sensing, we could see, some interesting things in position, navigation, and timing. There are quantum sensors that measure the magnetic field of the Earth. And so if we could develop, a map of that magnetic field, that could improve, both the safety and accuracy of some of our navigation. Okay, now let's talk about space for quantum, because for the quantum industry to grow and some of these technologies to become developed, we actually need space for it. So we could look at making satellite networks for a future quantum internet. As well, we could use satellites for quantum key distribution. And I believe there are some very interesting opportunities in quantum research and development that we could use space for. Okay, the next industry is manufacturing. So in manufacturing, we could look at developing new materials. So say you wanted to develop a new material that had a certain specific heat capacity, or it could withstand certain types of radiation or something like that. We could test those new materials in a simulated quantum environment before we actually produce them and test them in the real world. And that could save both a lot of time doing the research and development, but also a lot of money in producing, those early stage concepts and testing them with, a higher accuracy and more likelihood that they would succeed in being successful at what we're testing them for. As well, we could see lots of operational efficiencies improved through quantum optimization. Things like production, logistics, and supply chain are areas that quantum technologies can help with. So some of the quantum solutions we could see in this industry include simulation, optimization, and computing. The next industry is healthcare, and there are many quantum applications in healthcare. So much like new material discovery in the manufacturing industry, we could use the same quantum system to do drug discovery. We could test new drugs in a simulated environment before we then produce them and test them in the real world. As well, with optimizations, we could see improved medicines and treatment plans. And then, of course, data security is a big deal for the healthcare industry. Health data is the most expensive data traded on the black market. And some of the solutions that we see in the healthcare industry are computing, simulation, sensing, secure communication or quantum key distribution, and optimization. Next, let's look at how quantum could impact the travel, transportation, and logistics industry. So once again, we could see fuel efficiencies. We could see routes optimized. Once you factor in all the complexities that go into sending a ship across the Atlantic, you could look at tides, you could look at currents, you could look at wind and weather, you could look at humidity and air pressure. All these different things could be factored in, and quantum systems can handle larger data sets and larger amounts of variables. And then we could also see improvements in safety and navigation. And so some of the quantum solutions we could see in this industry are computing, sensing, as well as simulation. Okay, and then the finance industry. So in the finance industry, we could see, first of all, direct investment opportunities. We know that there are already some publicly traded quantum companies. So if you're interested in investing in those, they're available. There are, other ways of investing in companies. There are a lot of startup companies that are looking for either venture capital or private equity investments. But, aside from investing directly, there's also ways that we could improve the way that the finance industry operates. So we could see improvements in financial modeling, and we could see portfolio optimizations being done on quantum systems. As well, another issue that could be addressed is authentication. So if we had 100% secure communication, then we could authenticate things a lot better. So some of the solutions we see out of this industry would be computing, communications, and optimization. All right, so let's talk about hype again, because I did present some pretty interesting things, but I just want to remind you that quantum is not magical. Quantum is a real, technology. It's a real industry developing real solutions to real problems. But just be wary if you hear somebody saying that quantum is going to cure cancer and solve world hunger in the next 6 months or something like that. It might in the future. We don't know. We don't have that quantum system to see exactly what it can do and what it can't do. But in the meantime, I would just caution people to be wary of statements like that. As well, the timeline. So the timeline for some of these quantum technologies is different. So some of these things, like having a fault-tolerant quantum computer, that's like the holy grail of quantum computing. That is a little bit down the road. We're not sure, maybe, 5 or 15 years down the road. But other technologies are available now. There are other quantum computing systems, not fault-tolerant quantum computers, but there are like quantum annealing systems that are available today. D-Wave is offering quantum optimizations. They have a commercially available optimization program. As well, quantum sensors. There are some quantum sensors that are available as well. And so it's important to know about the timeline for the various technologies within quantum, and beware of the hype and some statements that people make. Okay, so let's look at the quantum workforce. So the quantum industry needs skilled workers to join the quantum industry to help build these technologies and develop them. So they're looking to upskill workers from other industries, not just developing, quantum doctors in universities, but they're also looking for people in adjacent industries that have transferable skills that could be used in the quantum industry. And it's as well, we're going to need non-technical workers to join the quantum industry. I'll talk about that on another slide. So there is a massive demand for skilled workers, and by 2045, it's estimated that the Canadian quantum industry will be worth $139 billion and account for more than 200,000 jobs. So far, the Canadian government has invested a little over $1 billion since 2012 into quantum technologies. And we actually have a national quantum strategy here in Canada, which the government has committed $360 million towards. And within that strategy, there are kind of three pillars here. We have research, which the government has committed 141 million, and that's for basic and applied research to produce new solutions and innovations. And then the talent pillar, the government has committed 45 million, and that's to develop and retain quantum talent in Canada and also to attract experts from outside of Canada. And then the commercialization pillar, the government has committed 169 million, and that's to turn research into products and services that are actually useful to Canadians and to the world. All right, so there will be a demand for technical workers to work on quantum technologies, but there will also be a demand for non-technical workers to join the quantum industry. So here are some examples of the technical roles that people could find in the quantum industry. So we could see things like a hardware or software engineer, a quantum algorithm developer, a quantum systems architect, quantum security specialist, quantum applications specialist, quantum metrologist. We'll need policy analysts, communications specialists, data scientists, database engineers, cryogenics engineers, circuit designers. So there are a number of roles in the quantum industry that are, they're kind of technical and they require some quantum knowledge, but there's also some adjacent jobs that might be transferable to the quantum industry if you could upskill a little bit on the quantum knowledge. Now let's look at, I made this specifically for this talk. So examples of quantum and space roles. So here are some examples of roles that maybe could be filled, in the space industry using quantum or in the quantum industry using space. This is the intersection of those two industries. So we could see satellite and spacecraft quantum systems engineer, quantum communications engineers, space quantum computer engineers. So like when I say space, and it seems like that's the only thing that's different from the slide before, it actually is a lot different to do quantum, to do any science in space because it's a different environment, right? We don't have an atmosphere in space. The temperature is completely different. There's no air to breathe, et cetera, et cetera. So getting a quantum system like a communication system or a computing system or even a sensing system, it's going to be a little bit different in space and most likely more complicated, but it would be different in space. And then we see also cryogenics engineer. We see that again. Quantum algorithm developer. So same thing as the previous slide, but for space applications. And then we see quantum application researchers. So this is like the quantum researchers, right? So people interested in cryptography, sensing, communication, and networking, but in space. And then we have pure science researchers in quantum, so astrophysics, space science, or if you study the early universe. And then I'd also like to talk to the non-technical people in the audience. So think of quantum as like an industry, just like any other industry. You're going to need the same kinds of people to fill the same roles in the quantum industry as you would in a traditional industry. So we still need business development managers, people who can do marketing and communications, salespeople, human resources, project managers and product managers, customer service representatives, legal specialists, business analysts, as well as operations experts. So I want to point you here. So for the job seekers in the crowd, I want to point you here to something called QEDC. QEDC is a consortium focused on the education of quantum. And they post jobs from all around the world. And they have, as far as I've seen, they have the most jobs compiled in one location out of any website that I've visited. And I have an example here. This is a screenshot showing some of the jobs, and you can see, Deloitte Consulting, Amazon Web Services, Atom Computing, and so on. Those are all the companies that are offering positions where they need a quantum person. Excuse me. So, if you're interested, you can just Google QEDC jobs or something like that. I also have the link here. It's quantumconsortium.org/quantum-jobs. And I want to point out some of the examples of jobs that we have on this job board. So I was so proud a couple nights ago, I was like, I'm just going to check and see if there's actually like a quantum and space job. And there was one. Okay, not a ton, but there was one. And it's PhD position, spaceborne quantum communication for a company called TSAT, and they're based out of Germany. There are some other jobs there. I mean, there's a ton of jobs, but here are some that I highlighted. So quantum research scientist for AWS, high-powered computing dev hybrid for Xanadu, technical writer for Q-Control, quantum technical sales engineer for Pascal, and laser engineer for Atom Computing. So you can see there's kind of a range there. And there are non-technical jobs available on their website as well. But sift through and see what tickles your fancy. They've got a lot on there. Some other consortia to look into here as well is the Chicago Quantum Exchange, Quantum Industry Canada, of which we are a member, as well as Elevate Quantum. It's worth checking out the different consortia just to see if they have a different job board than anybody else.
AJ, I had a quick question about that because you mentioned earlier by 2045, 200,000 jobs. That's the projection. And so I see these positions here now. This tells me these companies are actively recruiting now. So,
Yes.
Any idea how close we are? Is that 2045 a projection, or are we going to be even closer to that before that?
That's an excellent question, and it's hard to predict. My guess is that it probably will be a little bit quicker than what they've projected. I looked on QEDC just a couple days ago when I found the spaceborne quantum communication job, and they had 601 jobs posted.
Amazing.
So yeah, I mean, and we're helping to fill that gap, right, with Qubo. So we're hoping to help upskill people who can join the quantum industry and take some of these jobs, some of these, hopefully high paying and technical jobs as well.
Well, we've got some questions in the chat. I'm going to get to some in a moment, but I don't want to take away from your presentation.
No, it's all good.
So we've got some good ones coming. So please continue, and we'll get to some of these as they come along.
Sounds good. Thanks, Daryl. All right, so here's just a picture from Quantum Industry Canada. These are all of their member organizations. And so you can see the full members here. Qubo's down in the bottom left corner. I'm not sure if you can see my mouse right now. Probably not. But anyways, we're in the bottom left. I put a little arrow there.
We see your mouse. It's good.
Do you? Excellent. Okay. And there's some like really exciting quantum companies here. We see like Anion, Evolution Q, D-Wave, Isara, KI3 Photonics, QTI, the Quantum Insider, the Quantum Valley Ideas Lab, Cubic Technologies, SB Quantum, Xanadu, really 0 Point Cryogenics, like really exciting companies. All right, so take action. I don't like just telling people a bunch of information and not giving you anything practical to actually do with that information. So here's my practical slide for you. So take action. Remember, you don't need a PhD in quantum physics to join the industry. There's a ton of non-technical roles that will be necessary as well. Also, maybe you have a PhD in adjacent industry, and that's got transferable skills that you could use in the quantum industry with a little bit of upskilling. So develop a general understanding of the implications of quantum. Start building your quantum literacy now. You can educate yourself to ease the transition and make yourself more employable. Think competitive advantage, and you're competing against other people for a job, right? If you have some quantum knowledge, maybe that'll get you the job. And you can find quantum training programs to get you there. Now, if you're wondering about like, are there any quantum training programs available? Yes, I don't want to leave you hanging, of course. So as I mentioned, we will be putting courses and selling them through our website. But right now available, you can take our courses through Nate. And we are just announcing this. This isn't like, we didn't even do the press release yet. Like that's coming out on Friday, but we're going to be teaching our courses through Nate starting at the end of February, and we have 2 certificate programs available there, and these are meant to be upskilling programs. So we have a technical program called Quantum for Engineers. That would be for engineers and scientists, or anybody who has a technical background, but not really a quantum understanding. And then we have a certificate for executives. So this is meant to be a non-technical program. So we have Quantum for Executives, and that's meant for people who don't have a technical background and don't want to get into too much of the technical about quantum, but want to just know what's happening in the industry, why is it such a buzzword right now, and what do I need to pay attention to? And you can sign up for Nate through Nate's website. We have a link on our website as well on cuboquantum.com. All right. And then, as I mentioned about the soon to come e-courses, exciting for everybody who's here today and who actually signed up. Anybody who signed up will be sent a code for 30% off your first Qubo course once they become available. And in the meantime, we have tons of free access, blogs, videos, and more. Come check it out. All right. So I'm going to pose a reflection question to the audience. I know that you can't communicate directly with me, so I'll just give you a second to think about it. I'll take a sip of water. But which country do you think invests the most in quantum tech?
Why don't we get people to put that right in the chat right now? They
Sure.
can probably add their comments there.
Put it in the chat. Some people probably already know the answer, but
Let's see if we get any respondents there. That's a great question. Depending on where we are with the chat, what's the answer, AJ?
well, we'll continue on with the presentation to find out.
Oh, okay, got it.
What's your guess, Daryl?
Well, do I think invest in most in quantum technology? I'm thinking it's something not in North America. I think it would be something either in Asia Pacific, maybe. Maybe I'm wrong, but that's what my
I think you're right on track. I think you're right on track. Okay. So let's take a look. Section 3, it should be, not section 2, global quantum market. We're going to look at the investment in quantum as well as some notable quantum investments. Okay, so a little bit of an overview. So global investments in 2022 reached 2.35 billion.
Hang on,
in-
AJ. There's
Oh.
guesses in the chat.
Sorry, I don't know if I can see the chat.
No, I can see it. It's all good. Oop.
Oh, there we go.
There we
I
go.
brought the chat back up.
The guesses are China, Germany, USA, Canada, and Japan. The
Excellent.
suspense is building.
Yeah, pretty much all of those are in the top 10. I can't remember where Japan is on that list, but China, Germany, US, Canada, top 10 for sure. Good work. And one of those, I'm not going to say which one of those is the most. So somebody guessed the correct answer there. All right, so 2022 investment was 2.35 billion, dropped a little bit in 2023, 1.2 billion, but that followed sort of a global venture capital trend in 2023. And I believe that the numbers for 2024 were very good as well. And I mentioned earlier, so Canada's national quantum strategy is $360 million, and that's spread out over 7 years. And hopefully they'll inject more after that. And then let's look at some notable investments in quantum. So Quantinuum, based in Colorado in the US, raised $300 million last year. And the interesting thing to me about that is it put their valuation at about $5 billion. Pascal France raised 100 million euros, and that put them at a valuation of just over 400 million. Photonic Inc. here in Canada raised 100 million US dollars. And Sandbox AQ raised the most in 2023 with 500 million. They raised $500 million. But you'll notice even in the title of the article there, it's a Google spinoff. And so they have connections in the industry. And so that's how they can, create a startup and automatically get that kind of money. Because, companies like Qubo and the other companies I pointed out probably don't have access to $500 million right now. Okay. So here you go. These are the raw investment dollars in 2022. So these are the global leaders. And you can see right there, by a long shot, the leader is China. Okay. The US has caught up a little bit since then, but China is still the leader even today. So looking at this, so once again, this is from 2022. We can see Canada is number 6 on the list. Very respectable for a small country like us. And oh, I see a question in the chat. Does money evaluation matter in the quantum realm? That's a good question. I, so yes, in particular in the startup realm of the quantum industry, money is a very big issue. So valuation is what a company is worth overall, as opposed to the amount that they raised. So let me just back it up a sec here. So if we look at Quantinuum, they raised $300 million. You do a little bit of math to calculate, if they sold whatever, I don't know what it would be, like 20% roughly, or just under 20%, 18% or something. Then, they would sell 18% of their company for $300 million. And that means that 100% of their company would be worth $5 billion. So yes, the money valuations do matter in the quantum realm. Maybe not on the quantum scale in quantum, quantum mechanics. Probably doesn't know about money, but you never know. So looking back at our list here of global investors, so USA is number 2. Germany is number 3. So there we had, I think, the top 3 right there were mentioned. Somebody also mentioned Canada. Japan's not on this list, but I'll show you a map in a minute and we can see the current dollars that have been invested. And I believe Japan is on the map as well. So before we do that, let's just look at the same numbers. So this, once again, this is from 2022, but I took the numbers from the previous graph and I changed it into a percentage instead of raw dollars, because each country has a different size of gross domestic product, etc. So we factored in the size of their economy and how much they're investing, and we made their investment as a percentage of GDP. So when we do that, we can see which countries are investing a lot for their size of economy. And so in this graph, Israel actually jumps up to number 2. The Netherlands is up there at number 3, Germany number 4, and Canada jumped up 1 spot to number 5. And the USA is way down here at number 9. So based on their economy, they could invest more in quantum. In theory. Anyways, 2024, let's look at some current numbers here. So global investment map based on 2024. Okay, so somebody was asking about Japan. So Japan has invested 700 million. These are in US dollars in quantum technologies. Canada, our overall investment in quantum technologies is 1.1 billion. Once again, those are US figures. The US now They have invested $5 billion into quantum tech now. So that's up because in 2022 they had only invested three, so they've invested almost 2 billion more into quantum tech since then. All right. So that wraps up my part of the presentation. That's the preview of the job seeker's guide to the quantum industry, kind of like, the hitchhiker's guide to the galaxy. The answer is 42, by the way. Anyways, so if you're thinking you like space, you want to bring a planetarium back to Toronto, and you'd like to support the mission of Space Place Canada, please consider making a donation to them. I'm sure they'd be thrilled with just a small dollar value like $42 or something like that. So please feel free. Also, if you want to check out our courses, come to our website. If you want to sign up for our courses and get a Qubo and Nate branded certificate in upskilling in quantum technologies, then you can do that through our website as well as Nate's website.
Thanks, AJ. That's great. What great information. So detailed, and great information on future jobs and those prospects and the investments. Before we flip over to Katanya, I just thought I would share this one question with you as well, related to space projects. What criteria should be used to prioritize quantum space projects that offer the greatest benefits to humanity? Obviously, many of the jobs you spoke about, the technology, the investments, seems to be geared toward that. But is there anything on specificity that you can add on prioritizing quantum space projects?
That is an excellent question. And I would love to talk to the person who asked it. It's hard to answer a question like that without knowing a little bit more about the background and context.
Sure.
But my general consensus on something like that would be low-hanging fruit. Where is quantum the most advanced and positioned to help? And right now, I would say that would be in quantum sensing and quantum optimization. So if you have an optimization problem that you're looking to solve, I think I mentioned like satellite constellations. How do you use the minimum amount of satellites to cover the maximum amount of area or something like that? And then I believe there are already people who are working on mapping the magnetic field of the Earth using quantum sensors to be used in better position, navigation, and timing.
Okay. Yeah. And if we have any more questions like that too, people want to dig deeper, we'll try our best to see where we can get some more detail on that. Thanks for answering that. Okay, Katanya, the floor is yours.
If I may, there's a few other ones. I don't know if AJ wants to take them or if we want to take them together.
Sure, we can go through them if you want to do that now.
Yeah, it was up to you because we're happy to take questions for
Okay.
AJ's presentation and then take more questions after mine.
Sure.
I love questions.
Let's do this one then.
Okay.
This was one of the first questions, looking at developing navigation systems. Someone has heard that they're looking at developing navigation systems for aircraft travel. So how far away would you say we are from that being popularized for common use?
Ooh, that's a loaded question. Wow.
You got all the loaded ones today.
For commercial use, that's the tricky part because I know that there are people working on these things right now. I know, like we had a guest presenter come into one of our MyTax workshops and talk about his quantum sensors, and they're already testing them. Like I mentioned, measuring the Earth's magnetism to map out where you are in terms of position. If I had to give a number of years to that being popularized, I would say 5 to 15. I don't really know, to be honest with you, but it could be sooner because I know people are already investigating this. I have the feeling, I don't know explicitly, but people could be, doing proof of concepts and trialing technologies already.
Well, that's interesting. Well, and forums like this are great, right? Information is power, and the more we learn, the more we understand. So I'm hoping that helps answer that viewer's question, and I'm sure we'll continue to learn more about that. This one came. You talked a bit about security, data security. They're wondering how quantum can prevent hackers attack and protect your data.
Excellent question. So without getting into any of the technical details, quantum key distribution is a theoretically 100% secure protocol for transmitting information. And it requires a physical process to secure the data, as opposed to using a more difficult mathematical problem.
And I will talk about it in my presentation.
Oh, thank
Okay.
goodness.
Perfect. We'll park that one there for that.
Thanks.
Speaking of your presentation, why don't you start and we'll start taking some more questions after.
Yeah, because I think in the last couple ones, I will answer in my presentation.
Okay.
Yeah.
I'll stop sharing.
Great. Well done, AJ. That was really interesting.
Thank you. Thank you all for listening.
All right, so I will share. And I'll go into full screen. Okay. And how does that look?
Looks great.
Yep, that's good.
Excellent. All right, thank you so much. So we have got one more presentation to go. Hopefully you're all still awake. So I'm going to talk about quantum technologies in space. So the applications of quantum physics to the space industry. And as we already said, I'm the co-founder and CEO of Qubo Consulting. So my talk overview, I will first talk about what is the second quantum revolution. I will define what is a qubit, a little bit more detail than what I said at the start of our webinar here. And I will go over some space industry use cases. Then we will switch gears and apply quantum physics to astronomy and answer what is inside that star. It's like a game show, right? What's behind that door? And then finally, I'm going to wrap up talking about quantum communication satellites. What is the quantum internet? Maybe you've heard of that, maybe you haven't. I'm going to talk about the quantum encryption and science satellite mission, or KeySat mission. That's the part that I'm part of. And in that, the more technical side is defining what is quantum key distribution and what is trusted node QKD. And so we'll talk about that too, but just a little deep dive and then we'll pop right back up. So we'll get started with section 1. So what is the second quantum revolution? Well, wait a second. What was the first? When did we have the first quantum revolution? Well, all the modern electronics that we're using right now to have this conversation with the computer, the internet, cell phones, even solar cells, electric cars, things like this. Everyday life electronics were created using quantum physics, basically. These devices operate on the basis of quantum physics, but they're not necessarily using individual particles to do these operations. Other examples, the discovery of semiconductors, the creation of transistors. These discoveries were integral into the development of electronic components. As I already mentioned, the things you see on the screen right now, resistors, capacitors. The transistor was a huge moment in this technology revolution and allowed us to start making modern computers. Other examples of quantum tech. 1.0 tech, the wireless and broadcasting technology that we're using right now to have the internet, intersatellite communication. All of these signals are using different portions of the electromagnetic spectrum, light, right? The EM radiation. So light, radio waves, microwave radiation, that's all different forms of light. And we can use light to transmit information. We already do this, right? Also GPS. That's actually a quantum device. The global positioning units and all of the different satellites and on the ground, you're actually using an atomic clock to give an ultra precise timing to know your location on the Earth. So why are these all examples of 1.0 tech, right? It's because they're dealing with big signals, large samples, macro states. The behavior of atoms in quantum physics and in the quantum world is very different compared to the laws of classical Newtonian physics, right? If I throw a baseball, it's going to go straight, hopefully. Whereas in quantum, there's like a probability distribution of where that can go. You also have things like superposition entanglement, quantum tunneling, and we can harness these unique properties to do different tasks. So quantum 2.0 tech is using quantum properties and materials to do a task like computing, sensing, secure communication, even random number generation. So for example, we might be addressing individual atoms and then using those as the sensor, and instead of measuring signals from large collections of atoms, which would be 1.0 tech. Also, as we mentioned, there is something called quantum key distribution. So this is an ability to create a key, to generate an encryption key between two distant parties. And by using individual particles of light called photons, you can generate the key in an encrypted way that is secure, and you would know if a hacker is trying to learn your secret. I'll get more into that later. So that's an overview of what is 2.0 tech. And AJ's already been discussing all the applications and the different sectors and things like that. So that's just a little summary to get us back into it. So now, what is a quantum computer? So a quantum computer is using quantum elements like atoms, light, superconducting circuits to do the computing. And these special properties that a quantum computer has could potentially give it more computational power than a classical computer. And AJ and I are always very careful about our language. We're trying to not promise too much. This is a very powerful technology, and it is still in development. And so until we have a full fault-tolerant quantum computer, we won't know what is fully capable of these technologies. But there are quantum systems available right now, like quantum annealers and other systems that I have later, that can do operations, and you can see the power of these systems now. So quantum computers might be able to solve some problems faster and more efficiently because there's certain algorithms, code, that can be run on these quantum systems that cannot be run on a classical system. For example, you might have heard of Shor's algorithm. That's the way that a quantum computer might be able to hack RSA encoding. Also Grover's search. So searching large data sets, that's another very powerful thing that a quantum computer can do. However, quantum computers are not better at everything. Some operations are actually harder on qubits than they are on classical bits. I've heard trying to make a spreadsheet is not fun. So it's not like in the future, we're going to have everything replaced with quantum. We are going to have probably hybrid systems for everything. And maybe just those really hard problems get outsourced to the quantum cloud. And it's a good thing that quantum computers aren't better at everything, because that means there's some math that is also hard for quantum computers. And that's how you get post-quantum cryptography. So these are encryption algorithms that AJ mentioned. NIST has released 4 candidates recently. And these are harder mathematical problems that are supposed to be hard for both a quantum and classical computer to hack. However, it is not guaranteed theoretical 100% secure. Until you have a quantum computer to try hacking these codes, you won't know. And in the past, there have been PQC codes, encryptions that have been announced, and then they were very quickly hacked using classical computers. So again, you don't know for sure, but there are other ways to encode your information that is theoretically 100% secure. So what is a qubit? So a qubit, as I said before, is a quantum bit, but it's good to step back and first ask yourself, well, how do we traditionally, classically store information? So a classical computer, traditional computer, stores information in individual bits, 0 or 1. It cannot have a value in between, like 0.5. That would be counted as an error. The 0 and the 1, they have to be encoded, right? They have to be created. And so how do you do that in a classical computer? Well, you can have the flow of current is a 1 and no flow of current is a 0 through a transistor. Also in your hard drive, when you store memory, it's stored as 0s and 1s, right? So the polarity direction of the tiny little magnets that are in your hard drive disk, those are flipped, whether it's a 0 or a 1. Whereas a quantum computer is using quantum bits to store and process the information, or qubits. And now this is completely different. This platform is completely different because now you're using atoms or using photons to do the computation. And qubits can exist in a superposition state of both 0 and 1. So here's a question for the chat. See if anybody's alive or dead. No. Has anyone ever heard of Schrodinger's cat? The both dead and alive cat, which is depicted here as a cartoon. No cats were killed in this experiment. It was a thought experiment, first thought up in the 1930s by Erwin Schrödinger. And I'm just curious, type it in the chat. Yes or no, has anyone heard of Schrodinger's cat? And if you've ever watched the show The Big Bang Theory, you've probably heard it too much. And I'll see if I can see the chat. There's the chat.
We've got some yeses.
Ooh, yay. Excellent. All right. So.
And one no.
And one no. All right. Well, allow me to shed light on this concept. So it's, again, a thought experiment to try to conceptualize how crazy the quantum world is. So in the quantum world, you can have a superposition. You can have something in both one state and another at the same time. And so if you were to expand that to the macro world, the big world, it's as if you had a cat inside a box, right? Inside that box, there's also, in this case, the thought experiment, it has a radioactive decay element. And so over time, all right, the chances of the element releasing this hammer and the hammer breaking the vial of poison and therefore killing the cat, unfortunately, unless you don't like cats, and then it's fortunate. Anyways, so when that happens, the cat's going to be dead, but you don't know when that's going to happen because it's a radioactive decay. It has a probability associated with it. And over time, it's more and more likely that the vial of poison has been broken. But you don't know until you actually open the box and observe with your own eyes, your own consciousness, is the cat alive or dead? And so when the box is closed and there's no observer, this cat is in a superposition state of both dead and alive, which is just bizarre, but that actually does exist in the quantum world. And that's what the qubit is doing. The qubit exists in a superposition state of 0 and 1 until it is measured, observed. And I can explain what that means in more technical details if anyone's interested, what it means to observe something, but basically measure it. Or it gets disturbed by the environment. So noise, the environment. So noise in the quantum world, say your qubit is a superconducting circuit. Those need to be cryogenically cooled. So heat in the room is like noise. You want to isolate your device and make it as cold as possible. And so if it was to accidentally warm up, the qubits might start to cross over from being quantum to classical. And then that's being disturbed by the system, and then they wouldn't be in their superposition state anymore when they are classical. So noise also causes errors. Errors add up, and therefore your calculation will fail. Things like this. So noise is bad, environment is bad. You want to isolate your quantum systems as much as possible, usually. There are other systems that are more robust. It just depends on your platform. And this superposition state means that a qubit can have values that a classical bit just cannot have. Remember, if it had a 0.5 value, that would be counted as an error. So this actually opens up a whole new computational space that's just not possible with classical computers. But like I said, there are lots of platforms out there, and there's more and more being made every day. This is just a snapshot, and it's not an exhaustive list of different types of ways to make a quantum computer. So for example, you could address what's called the electron spin. So in an atom, you have particles inside, right? So you have electrons, you have protons, you have neutrons. You can address what's called the spin of an electron. It's a quantum property of that electron. It's not actually like a spinning top, but that's the analogy that we use. You can address the electron spin as a 0 or a 1. Spin up can be a 0, spin down could be a 1. In different platforms. So here you have superconducting circuits and all the different companies that work on that. You can have it in silicon and also what's called NV centers. That's nitrogen vacancy centers. Then you can also use atoms to do the computing. You can use trapped ions, also neutral atoms. And then you can use photons, like particles of light. So you got the photonic platforms. But take a look on the left here about how many companies are operating in this superconducting circuit space, and ask yourself why. Well, a lot of companies are using this platform because they were already very well established at microfabrication and nanofabrication technologies. And that's that quantum 1.0 tech that we were talking about. So companies that already know how to make microchips and things like that, they just kept making the circuits smaller and smaller and smaller. But if you've heard of Moore's law, right? The transistor just got smaller and smaller and smaller. But then eventually you were starting to make transistors and circuits where the path lengths were on the order of atoms. And now you were starting to have quantum physics and weird stuff happening, like tunneling, quantum tunneling. That's when a quantum particle can go through a potential barrier as if it's not there. It's as if someone just walked through my wall. My neighbor just walks through the wall and says, "Hi." That's not normally happening in our world, macro world, but in the quantum world, quantum tunneling is something we harness to do computing. But at the time, they didn't know that, right? When they were first manufacturing these things, it just weird effects were happening. They didn't know why. Anyway, so then, so this analogy or this similarity to the super semiconductor chip industry sort of ends here, though. So they do make the superconducting circuits on silicon wafer chips, but then that's where the similarity ends. And this is a photograph of one of these superconducting systems, and the qubits are actually on these little tiny pads, and the little wiggly lines are the cavities to link the different qubits so that they can talk to each other, but in a controlled way. So there's two ways that you can do computing. You can do computing with qubits, with digital gates, and you can do analog computing with Q modes, and it's called continuous variable. It's continuous versus discrete. If anybody remembers record players, so a record player would be like a continuous variable way of making noise, music, and CDs or MP3s or the digital radio, that's discrete variable. That's like the discrete way of making it. And so with the analog way, there's something called adiabatic quantum computing. So I'm going to deep dive just a little tiny bit for now, and then I'm going to pop back up and we're going to talk about the use cases of this quantum technology in the space industry. So just go to sleep for the next 2 minutes if you don't want to hear the technical side. So in adiabatic quantum computing, you have a system like a superconducting circuit, and you're able to program in your problem. It's usually optimization problems. That's a very typical thing that these systems can solve. And when you program your optimization problem into this circuit, you're trying to find the lowest energy state of your circuit, what's called the global minimum. Okay. And so if I was to make this into a picture, a cartoon, if we're the little ball and we're trying to find the lowest energy state, that would be way down here. So when classical search algorithms, our supercomputers now do this, they search for the global minimum. However, they have to search, literally. They have to go a little bit this way, a little bit that way, and then have thresholds. Like if the number is getting lower, keep going. But if the number is getting higher, stop, things like this, so that you search for the lowest minimum. However, they often will get stuck at a local minimum, and it's not the global minimum, because you can't search forever. It's a parameter space. You have to set limitations, you have to set thresholds, you have to set a time. So to get the best answer without waiting the age of the universe, you have to make some assumptions and some shortcuts. And you'll never be sure with a classical system that you actually do have the global minimum, the best answer. Now, take a quantum computer. An adiabatic quantum system, like a quantum annealer, can use quantum tunneling to find the global minimum, which is the best solution to your optimization problem. And what it is instead of the ball having to go up over the curve and down and to find the lowest energy state, the particle can tunnel. And so by tunneling, the system will always find the lowest energy state. It's as sure as a ball on the top of a hill wanting to roll down and be at the bottom of the hill, right? Gravity is ensuring that the ball would be unstable at the top and would want to roll down to the bottom, the lowest energy state. Same thing in a quantum system. It wants to be in its lowest energy state, and that's your solution. Okay, back up to the use cases. So how could that be applied? So we've got quantum optimization. We also have things called simulation and emulation. All of these have potential ways to help the space industry. For example, equipment delivery and procurement. Considering all the complex parameters like weather events, traffic flow, like we mentioned before, large data sets and handling multiple variables that have interdependencies is where these quantum systems really, really thrive. Also in simulation, you can have new materials design. So in space, we're always trying to find lighter, stronger materials. Also designing better batteries. I mean, when you're up there in space, whatever you've got is what you've got. It's not like we have an extension cord to go up there, right? So if you can design a better battery pack that gives you a longer lifespan or allows you to power more devices, that's really powerful. And you could potentially be simulating these things using a quantum system and instead of a supercomputer and be able to design potentially a better battery. And then we have route and resource allocation optimization. So you're improving fuel efficiencies, for example. You could do dynamic flight and cruise scheduling. So often it's very difficult to shuffle people in real time or equipment. These are the types of problems that quantum systems can help with. Also, assigning commercial airplanes to an open gate. The number of times I have been flying and I am stuck on that plane because we can't deplane because the gate that we're at isn't open. Yeah, there are literally quantum companies that have these problems on their use cases websites. Also, digital twins. So digital twins, that's when you make a digital model that is a twin of something in reality so that you can try out concepts. You can look at vulnerabilities, things like this without having to create it in real life. Or if it already exists in real life, it allows you to model it in digital land, right? These are very, very large data sets. And so if you can handle that with a quantum system, and you might be able to model more complex structures. Finally, there's something called quantum neural nets, neural networks, and you can apply this to weather prediction. And this is giving more accurate modeling with ultra-fast processing and execution speed. Sorry. Even though it's not that late, it's been a long day. Okay, so are there any questions about that? I know that was quite a bit of quantum tech.
We had a couple. I was going to take this one. I guess the infallibility, of quantum computers. If quantum computers are not fault proof, then how are companies like Google able to release quantum computer chips?
So there's different levels of quantum computers and different types. And when we say fault tolerant quantum computing, it means that it has certain qualities, like fault tolerant error correction, and things like this. And right now we are in the era of noisy qubits. So we can make qubits, we can make systems, but we have noise, we have errors, and so we can't run too long of algorithms. We can't run like lots and lots of gate operations because the errors will add up. And so it's limited in what it can do. However, because of this power of how different a qubit is compared to a classical bit, you have so many more potential applications that outperform or could potentially outperform a classical computer. So even though we only have, say, 50 or 100 or 200 qubits, depending on what the platform is, that can be enough to compute with like a supercomputer. So just think about that for a second. So my computer has an 8 gigabit memory, right? So that's 8 times 10 to the power of 9 bits. And I'm talking about 50 to 100 qubits that can over like, and that's not even a supercomputer. That's just my laptop. So that's how Google and other companies can be releasing systems, chips that have quantum properties. And if you're talking about the Willow chip in particular, that's also complicated.
That's for another time.
Yes.
Thank you. There was a question in there. I don't know if you can see it, and I want to make sure I'm actually asking this the correct way, because you talked about the 0 and the 1.
Yes.
What if you can prove the observations of 0, 2, and I see 1, 2 is infinite, or I'm thinking, are they saying half? Do you see that question?
I do see that. Yeah. What if you can prove the observations 0 to 1
2 is infinite, maybe?
2 is
That's what they
infinite?
mean?
I don't know if the 2 is supposed to be there. 0 to
Yeah.
1.5 is infinite. I don't understand the question. So whoever asked it, could you please rephrase and try again?
We can
No.
rephrase that. And also, by the way,
Yes.
this is super interesting. We can extend and keep going for everyone who wants to continue, as well as we continue to hear your presentation and still continue to ask questions. So I find it super useful. You talked about some useful applications already as well. And we talked about some other things. So I would say let's continue, and then I'll continue to, well, here's one more. Let's do one
Yeah.
more. Is the brain a quantum computer?
Yes, that's an excellent question. So I have colleagues that study quantum consciousness as part of their research. And that's one of the questions that they're looking at is consciousness and quantum related? I would say that the interactions in our neurons is on the quantum level, and that there are arguments to be made that there's quantum effects going on. And so I personally, this is where you start to go into philosophy a bit. I personally believe that our brains are like quantum systems. We are one of the most sophisticated quantum computers. And by trying, because basically a quantum computer is nature, right? Is nature computing, right? It's not creating it artificially. It's using nature to do the computing. That's what Richard Feynman first said in the 1980s, right? So yes, I think our brains are quantum.
It's fascinating. What a great response. Let's continue, Katanya. I'll continue to monitor the questions, and we'll carry on with your presentation.
Beautiful. Thank you so much. Okay, so what is inside that star? Let's apply some quantum physics to astronomy. And just as a side note, when I started my undergrad at University of Calgary, I started in the astrophysics department because I really wanted to learn general relativity, special relativity, and astronomy, and I love space. And then I found out that astronomy was more like data processing on a computer than actually doing things in space. And I didn't want to be an astronaut. So that's why I transitioned to being physics, because I was still able to do general relativity and special relativity, but now I was able to go into a lab and turn on a laser and, push a button and tilt a knob and see a reaction. I didn't like the idea of, the light coming from the star and that's all you got. So yeah. Anyway, so that's why I can cross over into the astronomy side and talk about this now. So we already use spectroscopy to identify the composition of materials and gases and things like that. We do this all the time. And there's devices, there's companies that exist. It's not it is quantum, but it's part of that quantum 1.0 revolution that's been around for a while. We can also learn the chemical makeup of a star by looking at its light's spectrum, its rainbow, right? So the famous Pink Floyd image where you take white light through a prism and it breaks up into a rainbow, or anytime you literally see a rainbow in the sky. So what's happening is the light, right? The light from the sun, for example, it looks yellow, but if you shine it through a prism, you see a full rainbow, you see a full spectrum of colors. That's because that's what is inside the light when you break it up into its colors, into its spectrum. And so every atom, hydrogen, helium, mercury, every atom on the periodic table has a unique rainbow. It's like a unique fingerprint. You can tell what atoms are inside the star, like in the gas, by looking at the star's fingerprint, the spectrum. So what do I mean? So here you have a picture of hydrogen gas being excited by electricity, okay? Just like a neon sign, but instead of neon gas inside, which is actually that bright orange, so if you see that color, that is neon. But if it's this color, it's hydrogen. It's actually a hydrogen sign. So you can go up to the store and be like, hey, your open sign is hydrogen, maybe. And then if you were to break that up into your different colors, you actually would see 4 discrete individual lines. You don't see a rainbow. You see a purple line, then a blue line, then a greeny blue line, and then a red line. And this was observed back in early 1900s, and it baffled the scientists then because it made no sense. Why are these discrete energy transitions happening in an atom? We thought atoms, were continuous. They didn't have this levels. Now, I don't want to go into Niels Bohr and everything, but this picture here is the Bohr model of the atom. It's one of the first models of our atom. We have a more sophisticated model now, but this is really, really good for understanding why you see these transitions. So you have, in the hydrogen atom, you have 1 electron, and you got 1 proton. And when that electron transitions from one energy level to another, because it actually does have discrete levels in the atom, it'll give off a photon. So if it goes, say, from the 3rd level here to the 2nd level, it lowers its energy level, right? And energy has to be conserved. Energy cannot be destroyed or created, right? So if the electron has lost energy, it has to transition into something else. So it releases a photon, which is this squiggly line you see here. And because there's discrete energy levels and there's only 1 electron, you only get these 4 lines. What about another element? So now look at argon. Argon has way more electrons, way more electrons. And now look at its rainbow. Its emission spectrum has a bazillion lines. It almost looks like a continuous rainbow, but it's not. You can clearly still see there's lots of gaps. So you can compare how complex a spectrum like argon is to helium. And it's all because of the atom. And so every single element has a unique fingerprint like this. And so what we can do is we can observe the light from a star, and you see the spectrum here. And then instead of seeing the emission spectrum of the gases that are actually around the star and near the star, you're going to see the absorption. You're going to see the opposite. And so you see these dark lines. You see the bright, bright, bright rainbow. And then you see these dark, dark, dark lines. Those are the absorption lines of those elements. Why is it absorption? Why is it dark? Well, it's because the gases that are on the outer layers of the star are cooler than the very, very inner core. And so they absorb. They have energy they're in a lower energy state. They're cooler. So they have the ability to absorb some light. And so when they do that, they do their energy transitions, right? And then they re-emit those photons, and they get re-emitted in a random direction, not necessarily towards your telescope. So that's why you see the dark lines. And so you can line up the different spectrum, and you can identify what's inside this star. So you can see there's hydrogen, helium, and sulfur, because if you add up all of these lines, they add up to the absorption lines. Also, you've probably seen the aurora borealis, I hope, the northern lights or the southern lights. That's this picture here. What you're seeing with your own eye are gases that are being excited in our atmosphere by solar flares, and the gases are being excited, so they're emitting their rainbows, right? So red is usually hydrogen and also oxygen. Green is also oxygen usually. And if you see purple, it's usually nitrogen. All right. So that's how you can identify what's inside a star. So now we're going to transition to the last section about quantum communication satellites. So here's another reflection question for the audience. See if you're all awake still. What comes to mind when you hear the term quantum internet?
That's an interesting question, Katanya. I think something super fast, like faster than ever before, but that's just my layperson thinking.
I like it. I could see where you're going with that. People have talked about entanglement as faster than light communication, so I could see where you're going. You always have to have a classical phone call, even when you do have entanglement, and so that's what is the speed limit. So you can't have faster than light communication. But that's a good guess. Are there any other guesses in the chat yet?
I'm just waiting for the
The relay. I know, I love
it's,
this.
it's always a bit delayed. Faster processing speeds is one of the answers.
Oh, there you go. Yeah. Yeah, that's true because the quantum internet would involve quantum systems like quantum computers,
A
which
very
would
big
have
internet
faster.
or a very small internet is our other answers.
I love it. I love it. All right. Well, those are excellent answers. Basically, the quantum internet is like the classical internet, but everything is quantum. So what is the classical internet? It's always good to define that first, right? Just like when we were trying to talk about a qubit, defining what a bit is first. Let's just make sure everybody knows the classical internet, it involves fiber optic cabling, right? It's sending light, infrared light at 1550 nanometers all around the world. And that light is holding the classical information. So that's the fiber optic cable, the yellow cable you see here. We've got tons and tons of data, amplifiers, and storage devices all around the world. You can see this is this picture is a false color picture to show the length of the fiber optic cables that are laid under the water that connect up all of our land masses to make the internet. And if it's a red color, which is like over here and over here around India, or it's very confusing, around Africa and around China, you've got 36,000 kilometer length cables. So right now, our fiber goes close to 40,000 kilometers. That's how far the light has to go to get to some regions, okay? Keep that number in mind, 40,000 kilometers. And then we have, for example, this is a picture of Starlink by SpaceX, all of the network of satellites that are going around the Earth right now. That is also the space component of our internet, right? So we have ground and we have space. Well, if you want to establish a quantum link over a distance, say between Canada and Australia, you cannot use a 40,000 kilometer cable. You are limited in cabling to only 500 kilometers roughly. Quantum information is very, very, very sensitive, and it cannot just be amplified like our current applications. That's for technical reasons, which I can go into later. And so you have a distance limitation of how far you can send quantum information to make the quantum internet of about 500 kilometers through fiber. So when you need to link further distances, we need to go to space. And so there's a space race going on, and it's the quantum space race. And even though this is an image that's from 2018, it's still very, very relevant information because a lot of these missions are either ongoing or still about to launch, things like this. So you can see this is a handful of different countries that have space missions. They all have different satellite types. They're in different orbits. Some of them are in low Earth orbit, some medium, some geo. You've got a lot of missions from China. They're up to like number 6, I think, number 7 quantum satellites. So Metius was one of the more famous ones that demonstrated a lot of things quantum. And then we've also got Canada's mission here, the KeySat mission, which we'll talk about in just a minute. And you might notice that there's this the beam, right? The beams of light, and some of them have the skinny end at the ground station. That's what these domes are, right? So these quantum ground stations, they're just like observatories. except you've got quantum devices as well as your telescope. And so you have your telescope housed inside, and then if the beam is skinny at the bottom and larger at the top at the satellite, that means it's a quantum uplink, because light diverges, right? It spreads as it travels. And so the Canadian mission is primarily a quantum uplink channel, whereas other missions, for example, the one in Japan here, was a downlink channel. So you have the source, the quantum source on the satellite, and then the quantum receiver is on the ground. So as I said, the technologies that are involved, you have a quantum ground station. So current optical ground stations with their telescopes can be converted to being quantum, as long as it's the right wavelength, obviously, to collect the light, and replacing the detectors and the transmitter with sources that are quantum and devices that are quantum. So what does that mean? A quantum detector is like a single photon detector. So, and a quantum source would be like a single photon source, or an entangled photon source, or a quantum dot source, things like this. So on one hand, you have the ground, and then on the other hand, we have the satellite. And so for the satellite, also you can have high altitude platforms. So for example, we at IQC, Thomas Yanavine, the prof involved in this mission, did a proof of concept demonstration using an airborne platform, which was on an NRC plane. They removed the door of the plane and strapped 2 PhD students inside. Yes, they had harnesses, so we didn't want to lose them, just for their PhD work. And they had their telescope, and it was doing a quantum uplink. So the telescope was the receiver inside the plane. And that proof of concept worked back in 2017. And so 2018, the KeySat mission was announced with CSA. We'll get to more of that in just a second. So these quantum space links, they have physical limitations, okay? So often we're having to limit it to nighttime operation. So the sun is really bright, right? Trying to isolate your single photon source signal from a gazillion solar photons is really hard. It's already hard enough doing quantum physics, but doing that is harder. Also, we're going to use a sun synchronous orbit usually, so that we are at the opposite side of the sun. And so you're usually linking around midnight, your local time. And then the daylight operation has been demonstrated at 1550 for like free space connections on the ground. I need to double check if there's been daylight operation to space. I think so. But it's very, very difficult. And so there are certain colors, certain wavelengths that you can work at where you can filter the light and find your signal. And so the telecom wavelength of 1550 is very convenient for that. Also, you depend on the weather when you're using quantum links. Unfortunately, they don't work right now through clouds, through rain. There's too much loss. You have to have that signal to noise ratio relatively high to have a good signal to be able to do something quantum with your final signal. I'll say signal 5 times. And you need clear skies. So there are certain locations on the Earth that are going to be better than others for quantum links. And the loss sensitivity. I already mentioned how we are very limited in the distance that you can send quantum information. Quantum light is very sensitive to loss and disturbances. You can't just turn up the power to overcome the loss, because then it's not quantum anymore. If you use a classical amplifier, you have to use a quantum amplifier, a quantum repeater, quantum memories. These are devices that are complex. They're under construction, under development right now. And the idea is if we could put one in space, then that would help to store and relay the quantum signals for inter-satellite communication. So the longest hybrid quantum space network currently to date demonstrated was by China in 2021. Oh, that was the publication. So it was with the Mishia satellite that I mentioned. There was 2 ground stations, and then one of the ground stations was also near a fiber network node. So then the light went from satellite to ground and then to fiber. So in the end result was linking one quantum ground station with the, Shanghai, for example, down at the bottom. And so that entire length of channel, including the space, is about 4,600 kilometers, which is insane because during my PhD, I was doing quantum entanglement measurements and demonstrations in my lab, and my optical bench is a couple meters, right? And so with all of the mirrors and folding the light, maybe I got to 3 meters. They demonstrated quantum entanglement over 4,600 kilometers. Yeah. So this is where it gets cool because we're crossing over quantum and space. That's the intersection that we don't have the physics for yet, right? The physics of the very, very tiny explains that very, very well. And same with the very big, explains very big very well. But when you try to combine the two, that's where you need a grand unified theory, a theory of everything, something that would explain black holes as well, right? So we can start to test theoretical calculations that try to predict quantum effects in relativistic settings, because satellites move really fast. That's what our project goal right now is at IQC. Just track a satellite as it flies over your head really fast. So not only do we have to track the satellite, we have to get single photon signals to it and from it. But it's possible. It's been done, and we will do it. So what is Canada's first quantum communications satellite? Hands up if you know. Hasn't been launched yet.
I don't know that. I don't know the answer to that one, but we can wait for the answers.
I've been name dropping it throughout the presentation.
Oh, okay. Is that KeySat?
KeySat!
Yay!
There we go. So the main mission objective is to demonstrate quantum links and to do quantum key distribution from ground to space in Canada as well as globally. And we have national quantum ground stations. There's one in Waterloo. There's the primary ground station at the CSA headquarters, the Canadian Space Agency. We also have one in Calgary at their observatory. And we have some international partners as well that are going to be linking with KeySat. And so again, the main objective, one of the main objectives, is to distribute quantum keys between 2 ground stations that are at least 400 kilometers apart. And that will be done just with the CSA and the Waterloo ground stations, because they're already more than that distance apart. And the transmitter telescopes, as you can see in this picture here, are very compact. It's only an 8-inch refractor. You want to send a very well collimated, parallel light beam that's not going to spread as quickly as possible, right? So if you have a large beam on the ground, then it won't spread as quickly up to the satellite. Whereas if you start with a very small, very narrow beam on the ground, by the time it gets to satellite, it's massive due to diffraction. So with an 8-inch refractor, by the time the beam will get to the satellite, it'll be several meters. And we still have to capture the light into the single photon detectors. So that's enough signal, luckily. And that was what our proof of principle concept was testing, this airborne demonstration, which is what's shown in the photo. We'll be studying quantum links, entanglement in relativistic settings, and some other new science demonstrations, seeing how adaptive optics can help with these quantum links, improve handling the atmosphere, weather, things like this. And this picture here is a cartoon of the receiver. So the light comes in the telescope, which is this collector lens here on the far right. And then you see 4 black boxes. Those are the single photon detectors. And there's 4 channels. You can see them labeled VHAD. They stand for the polarization angles, right? So vertical, horizontal, anti-diagonal, and diagonal. So in this encoding, we are using polarization to encode our zeros and ones, to think of it that way. You always have to pick a property. You could use light, you can use time, you can use polarization. So that's what's happening here. And you can see that the DA are physically rotated relative to the HV. That's not your eyes playing tricks on you. They are. It's physically rotated 45 degrees because polarization has a direction, right? Is
I
there
have
a
a
question?
question.
Yes.
Yeah, and I think it makes sense here. Do the photons interact with the qubits as particles, or
Sorry, do the photons interact as particles or?
do the photons interact with the qubits as particles or as waves?
Oh, I see. I see. Okay. Well, the photons are the qubits. Um, and the photons can act like both a particle or a wave, depending on how you interact with it, how you measure it. So in this case, because we're using single photon detectors, that means we're measuring in the discrete variable regime, discrete digital. So they're acting as particles. But you can swap out these detectors for other detectors. For example, there's a homonine detector, and then you're measuring in continuous variable, and then it acts like a wave.
Okay. Also, I'm just going to do a quick time check. We're at 8:46.
Okay.
And I want to be able to still give you the platform to take us to the end. And then if there's still some room for some more questions, we can do that.
How about I end on this slide, and then I'll go to my final slide.
Sure. Sounds good.
Okay, cool. So for those techies in the audience, what is trusted node satellite QKD? Okay, so why do I keep saying this is secure and this is so wonderful? If you've heard of one-time pad encryption, that's the type of encryption I'm talking about that's 100% secure. And so in order to do one-time pad encryption, you have to have a key shared between two parties. Then you implement that encryption and it's 100% secure. So the bottleneck is the key. In the olden days, we would literally transmit the key with some sort of secure carrier. Like literally think of someone with a briefcase handcuffed to their arm, traveling from one place to another. But instead of physically sending a person or a message that way, we can create the key using photons and satellite and a ground station. So in this configuration, you have a satellite that makes a connection with a ground station. Then it goes, flies to another ground station and makes a connection with that ground station. And so because the satellite makes both of these connections, the satellite knows both of the exchanges that happened with both ground stations. So there's actually a key that gets made with ground station A. There's a key that will get made with ground station B, and the satellite knows both of those. But the two ground stations only know their own key, right? A only knows A, B only knows B. So what you do is you XOR, it's an operation in binary operation, you XOR the two keys. The satellite can publicly announce that XOR. It doesn't make any sense to anyone unless they already have one half of that. So it's safe to announce that. And then, for example, ground station A can XOR that public announcement with their key, and they will get back the B key, ground station B's key. And that's how trusted node QKD works with one satellite. And this is the configuration that we're using for the KeySat mission. So it's going to be trusted node QKD. Yes, so that's that. And I will just skip that and go right to here. So thank you so much for listening. And sorry I talked too long. And if you'd like to, please consider making a donation to Spaceplace. We would really love your support. I've been a member of Spaceplace since 2019, before they were officially a charity. So I feel very honored to still be part of this organization, and I'm very, very proud to be able to support them. And if you would like to know more about Qubo, once again, here's our website, and there's lots of exciting resources there to check out. Thank you.
Thanks, Katanya. And no, you didn't talk too long. It's great. We could still listen to you. I know there's lots of information still to share. That being said, because there's a few questions, I thought I would throw these back at you to see if you, between you and AJ, you can answer these. The questions on photons. Do photons interact with the qubits as particles or as waves?
Yes, so that's the one we were talking about before. So the photon is the qubit.
Oh, yes. I
Yes.
answered that already. Yes,
You're
thank you
good.
for that. Got it. We're good. Check. What happens when the geopositions changes and the east becomes north?
Ah, very good. So when you're working with polarization-based encoding, you always have to have a frame of reference. And so you have to choose, is it the ground or the satellite that's defining that frame of reference? And so that's how you deal with the fact that the satellite could be in an orbit where its north is not your north. So you have to, you actually would use another beam of light to tell you what's the orientation of your satellite.
Next question is, how do you isolate the photon / cube?
Yes. Excellent question. So you isolate the photon in color, in time, and in space, basically. And maybe polarization too, if it makes sense. So you use filtering, you use spectral filtering, special pieces of glass that only lets through a certain narrow passband of light at a certain wavelength. That will cut out all of your background noise you don't want. Then you have time. So if it's a source that is like a pulsed source, then you know there's an arrival time that you're expecting, and so you only look for your photon in that window. And then you got spatial. So spatial is spatial mode. So literally you put a like light that you don't want to collect from everywhere else, you put a pinhole. And so it only allows a little tiny bit of light to filter through.
I think this question is good for AJ. It's in regards to business in terms of how can a company get started with quantum?
Oh yeah, thanks, Daryl. Yeah, excellent question. So like we kind of tailor our content towards these kinds of organizations. And so what we recommend for a business looking to get into quantum is first of all, figure out who's going to be the quantum person in the organization. You know, if you don't have a willing volunteer, you can volunteer them to be the quantum, you know, advocate. Because it's good to have somebody who understands about the quantum industry, has their finger on the pulse, understands what the developments are, and can notify people when action needs to be taken. And then, so once you've identified that person, I would suggest setting aside a small training budget for that person and rotate it into regular trainings so that you know, that person is up to date on quantum. And you know, if any businesses are interested in trialing like a proof of concept or having internal training provided or having us come speak at an event or something like that, please reach out to us. Like we're more than happy to help. That's what we're here for.
Now, my next question, this one's super technical. So I will read this and you let me know if I'm actually relaying it properly. In terms of simulations, what kind of decrease in solve time for ray tracing or view factor calculations could we expect?
Yeah, I saw this question pop up while AJ was talking, and I'm like, this is not related to what you're saying. Okay. This is a prepared question. Yeah, excellent. So I need a little help from the audience. I'm familiar with ray tracing. Are you talking about like optical ray tracing of like a telescope, like simulating like optical paths? And I don't actually know what view factor calculations. I'm one of those weird people that actually says when I don't know something because
That's
I
good.
find it goes way faster and then I just understand more because I ask questions.
That's great.
So
That's a great answer. We'll try to get some clarity on that for you for sure.
please.
There are a couple other questions I had as well in terms of, and you talked a lot about business and you talked a lot about initiatives that the government's doing in development for communication system networks, etc. But ethical considerations that govern quantum technology for space applications. I'd imagine there are aspects of putting in guardrails to make sure that this flows in the right direction and there's guardrails that keep things on track because it's such an important and evolutionary opportunity.
Definitely. And I would say that countries' national sovereignties are like integral to this because if you have your own quantum secure network, right? Like that's gonna be very important for your national sovereignty, for your national security. So I can see the ethics of how quantum tech and space will cross over in a lot of aspects.
Okay, I can come back to that last question we talked about tracing. They clarified, yes, it was simulating optical paths. That's how they clarified it.
Perfect. Okay. So Right now, you can run ray tracing, I'm pretty sure, on just normal computers. So I'm not really sure if a quantum computer would actually help, because if it's not, unless it's such a complicated problem and you have an extremely large data set and you've got a lot of variables to consider, that's where the quantum system would start to shine, right? And once you've identified that you do have a problem that you want to try on a quantum system, it's not the easiest thing to map it to quantum, right? So to take your classical problem and then map it to a quantum system. However, there are companies that exist that have platforms to help you with that, right? They have use cases and they have algorithms, sample algorithms to show you. For example, traveling salesperson problem. If you have multiple delivery locations and you want to minimize the fuel usage and minimize the time and the distance and things like this, that's a type of problem that can be mapped very easily to a quantum computer. And so they'll have online resources to help you with that. I haven't seen one yet for ray tracing, so that's why I can't help more with that.
Okay. We've got time for maybe a couple more questions. This one just came in as well. In terms of job opportunities, and if I wanted to become a software engineer in quantum computing with a CS background, I'm assuming that's computer science background. What other background would help me to jump into quantum computing a lot smoother?
Do you want me to answer that, AJ? Yeah. Okay. So there's going to be different levels for a software engineer. If you want to get into the hardcore programming a quantum computer, then that would require understanding technical side of qubits and gate operations, and so this is crossing into linear algebra, because there's matrices and things like that. Quantum mechanics is basically linear algebra, so background in a little bit of math. And then there's a lot of online resources that help coders to become quantum coders, basically. There are several different platforms that have tutorials, videos, code samples. You can get free time and access to try out a quantum computer for yourself. If you want to know more, please reach out to us and we can connect you with some people.
That's great. This has been fascinating. I've learned so much, and also we have maybe about a couple minutes left. I thought I would just throw it back to you guys one more to wrap it up with a nice bow. Give you each last maybe 30, 40 seconds each, just to anything else that you want to add and to leave with our viewers. And Katanya, I'll start with you and then over to AJ.
Okay, great. Well, I think the one thing I'd love to say is that anyone can be a part of this industry. It is a new industry. It's emerging right now. There are real people investing real dollars, as AJ mentioned, and there are real commercializable technologies that you could start to explore right now. So I think if you're wondering if this is like a pie in the sky, oh, it's going to happen in 30 years. No, it's actually happening right now, and your competitor might already have it. Thank you.
Yeah, that was excellent, Katanya. I don't know what I can add to that. I feel like, don't be hesitant, don't be scared. There's nothing wrong with not understanding something and exploring it for yourself. Like I've pivoted careers a number of times in my life, and it's very fulfilling and rewarding once you do it. And I encourage anybody who's thinking of making the leap, do it.
That's great. That's a great way to end it. And to one of your points at even the beginning, being willing to learn is half the battle, and to be open to that. And for us here again, thank you so much for partnering with us at Space Place Canada to present such a very thoughtful presentation. We've always said, imagine a place where the next generation of Canadians can discover the infinite possibility of science and exploration. And this is all part of that. And you've answered that question numerous times in so many ways today. So thank you again, AJ Sikora and Katanya Kuntz, for being part of this. Of course, if anyone wants to get in contact with you, you have your website information there at Qubo Consulting, and then at spaceplacecanada.ca as well. If you want to become a member, give a donation and help us see the future in terms of one day having a planetarium, and we can talk about all this cool stuff under one big fancy roof one day if that happens. So again, thanks to everyone joining from around the world, and for our Space Place administrators and members, and also again to Katanya and AJ. Have a great night, everyone.